Hey there everyone, this is the second video in the installment about chemical bonding, and today we're going to be going over the basics of covalent bonding and how to draw basic Lewis dot structures. There are some Lewis dot structures in which the central atom violates the octet rule, which I covered extensively in the previous video, but we're going to cover that in the next two videos when we talk about molecular geometry and polarity, and molecular polarity. So let's get right into it with some basic covalent bonding. So on our periodic table here, we see that there are some elements that occur naturally as diatomic molecules, some of which include chlorine, fluorine, oxygen, and nitrogen. These are all perfect examples to illustrate different types of covalent bonds. So let's start with chlorine, for example. Chlorine, indicated as Cl, has 7 valence electrons. We covered how to draw Lewis dot diagrams in the previous video, so I'll just quickly do that for both of my chlorine atoms here. And each has 7 dots. Sorry, this should be on this side. Each has 7 dots to indicate each of its 7 valence electrons that it can use in bonding. So what happens in a covalent bond is the difference in electronegativity between the two atoms, which states that how much a nucleus wants to attract an electron to itself, with fluorine being the most electronegative, meaning that it really wants to hog the electrons to itself when it shares electrons with another atom. We'll get into that more in this video when we talk about bond polarity. So when the electronegativities are equal, because chlorine and chlorine are the same atom, obviously, we form a non-polar bond. So this line is used by convention to indicate that these electrons are being shared in order to complete the full octet. So we count this as 2 electrons, 1, 2. So when we try to look at how many valence electrons each atom has, we can just count it as 2. 1, 2, 3, 4, 5, 6, 7, 8. We have a complete octet on this chlorine on the left side. 1, 2, 3, 4, 5, 6, 7, 8. We complete the octet in both chlorine atoms, meaning that we have the most favorable electron configuration. This is different from ionic bonding when electrons are completely transferred, but that's a subject for a different video. So this is a single non-polar covalent bond. So let's just focus on how many bonds. Single means 2 electrons being shared in that bond between the two atoms. So as I said, oxygen is another example of an atom that occurs in as a diatomic molecule in nature. So let's take a look at that. So let's draw our 2 oxygen atoms. We know that oxygen has 6 valence electrons because it's in group 6. So I'll just write this as shorthand because we have 2 of what are called lone pairs, which I'll talk about briefly, and 2 single electrons here. So lone pairs, single electrons. So as you can see here, we can form a single bond between these 2 single electrons. Does that satisfy our octet? 1, 2, 3, 4, 5, 6, 7. No, it doesn't. And you could just do the same in the other oxygen atom. What if we draw another bond between the 2 single pairs of electrons so we share that pair as well? We can rewrite our work like this. 1, 2, 3, 4, 5, 6, 7, 8. That's good. 1, 2, 3, 4, 5, 6, 7, 8. We satisfy the octet rule in both atoms, meaning we have the most favorable electron configuration in both oxygen atoms, which is why this is the most favorable structure of why oxygen occurs as O2, diatomic in nature. Chlorine occurs as Cl2. So this is what's called a double covalent bond. Both of these bonds are non-polar because oxygen, although it is one of the most electronegative atoms only behind fluorine, 2 oxygen atoms are obviously the same, so they have the same relative electronegativities, so they will share electrons equally. If we were to represent that in the bond, each pair of electrons would be in about the center of the bond, of course. So now we're going to take a look at one last atom, nitrogen, as an example of a triple nonpolar covalent bond. So nitrogen, as I used as an example, in the last video, has 5 valence electrons. So we can have one we'll draw it like this. We'll have 1, 2, 3, 4, 5, just because it's easier to draw the bonds. So now we can make one single bond, but we already know that's not going to satisfy the octet rule, because if oxygen had 6 valence electrons and a single bond didn't satisfy its octet, then why would one single bond in nitrogen with 5 valence electrons satisfy that octet? So we'll draw another bond and another bond. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We can rewrite our structure using a triple covalent bond. These are three bonds between the same two atoms, and we have these lone pairs. These lone pairs are just non-bonding electrons, and they become very important when determining molecular polarity and molecular geometry, which we'll talk about in 2 videos. So a quick note about the lengths of these bonds. As you might imagine, the single bond, because it's only one metaphorical piece of rope holding 2 atoms together, will be the longest. So in terms of length, from shortest to longest, the longest will be the single, because it's one bond holding 2 atoms together, then the double, then the triple. I'm talking about each individual bond. We have short to long. So these are all non-polar bonds right here, because they're between the same 2 atoms. So here the electrons will be shared equally, and the electrons would be shared equally here. But that's not always the case. So now we're going to take a look at one of the most prevalent molecules in all of life, water. So everyone knows that water, or should know, that water has the chemical formula of H2O. So if we draw O, we have one of them, and then H, and another H, because we have H2, and we write the valence electrons, we can see how the atoms in water are bound to each other. So hydrogen, because it's in group 1, although it's not an alkali metal, will have only 1 valence electron because it has 1 electron in total. We'll draw another, and then as we've said before, oxygen will have 6 valence electrons. So we will write our 2 lone pairs, and then our 2 single electrons here. Although they're not directly on the sides of the atom, this is just easier to draw. So we can draw 1 single bond, and 1 single bond here. Let's rewrite our work. This is the Lewis dot structure for water. Lewis dot structure. What a Lewis dot structure is, it shows how the atoms are bound to each other, but it does not at all show the orientation of the atoms in 3D. That's what molecular geometry is. This is a big misconception amongst chemistry students. This is a very important distinction to know. I said I was going to talk about bond polarity here, and this is a perfect example. So, for those of you that have studied biology and the electron transport chain, you may know that oxygen is the final electron acceptor in the mitochondria. Why is this? Because oxygen is one of the most electronegative atoms. As I stated before, electronegativity is the tendency of the nucleus of an atom to draw electrons towards itself when it bonds with another atom. So let's take a look at the bonds in water. We have OH and another OH here. O bound to H. Because oxygen wants to hog all the electrons to itself, the electrons shared in this bond would be closer to they would be physically closer to oxygen. So electrons, as we know, have a negative charge. So that means that this oxygen, even though its octet would be satisfied if I were to draw water structure again, I would have another lone pair here. Oxygen would actually become partially negative. This is a delta, this is a lowercase delta, it's a Greek letter. It would become partially negative. This is called partial charges. Another way to indicate this, if we were to draw this OH, or this HO or OH, it's the same thing, bond, we would draw an arrow and we would have a plus next to the partially positive and an arrow pointing towards the more electronegative atom. As you might imagine, since electrons are farther away from this hydrogen, it will become partially positive. This is the basis of hydrogen bonding, which we'll cover in a much later series, but it's also very important in our study of chemistry. So this is a polar covalent bond, where the electrons are not shared equally. So we already took a look at the Lewis structure of water, which shows how the atoms are arranged on a flat 2D surface, but they do not at all show how the molecule actually looks in three-dimensional space. So let's take a look at a couple of more Lewis structures. So let's look at PF3. This is phosphorus trifluoride. So a quick, easy way to draw Lewis structures is based solely off of drawing based on valence electrons. So let's count how many valence electrons each of our atoms has here in this molecule. So phosphorus, as we know, has 5 valence electrons because it's in the same group as nitrogen. So phosphorus will have 5, and then fluorine will have 7 because it's one of the halogens. All the halogens have 7 valence electrons in the same group as chlorine, bromine, iodine, etc. So it has 7, and then we have 3, so 7 times 3 equals 21. So 5 plus 21 equals 26. This means we have to show 26 valence electrons in our structure. So let's draw it based on our Lewis dot diagrams. So if phosphorus has 5 valence electrons, its Lewis dot diagram will look like this. Then fluorine with 7, and then 2 more fluorines also with 7. And now we see that we can make 3 single covalent bonds. So what's important in Lewis dot structures is counting up and make sure you have the correct number of valence electrons in your structure. As I've said in previous videos, in the previous video, valence electrons are the only electrons that participate in chemical bonding, so they're the only electrons that are really relevant in our discussion of Lewis dot structures. So let's count. 1, 2, 3, 4, 5, 6, 7, 8. Remember, we count a single bond as 2. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We have 26 valence electrons, meaning this right here is the appropriate structure for phosphorus trifluoride. Let's take a look at another example. So we have H2S. H2S is hydrogen sulfide. So let's use the same principle that we used before when we were drawing the structure of phosphorus trifluoride. So we can start with our central atom S. Now, a general rule when drawing Lewis structures, the central atom will always be the least electronegative, with the exception of hydrogen, because hydrogen is less electronegative than sulfur. But again, it is the exception because it has only 1 valence electron and cannot act as a central atom. So we'll need our periodic table again here. We know sulfur has 6 valence electrons because it's in the same group as oxygen, and oxygen also has 6 valence electrons. So let's count 1, 2, 3, 4, and then 5, 6. Then hydrogen we know only has 1. Another hydrogen only has 1. So we can draw our single covalent bond here. And remember, although I just drew the Lewis dot structure based on convention that would give this a right angle, that does not at all mean that the physical molecule has a right angle there. Again, that's a very important distinction to make. I could rewrite it this way, and they would be equally valid Lewis structures. The position of the atom doesn't matter in Lewis structures, but it only matters in molecular geometry. So let's count our valence electrons here. We said that hydrogen has 1 times 2 hydrogen. It gives us 2 valence electrons. And then sulfur has 6. We should get 8. So 1, 2, 3, 4, 5, 6, 7, 8 valence electrons means that this is the correct structure for hydrogen sulfide. So this is not an exhaustive video of Lewis structures, because there are some exceptions when we talk about resonance, when we talk about formal charge, and exceptions to the octet rule. These will come in the next 2 videos. In the next video, I'll talk about resonance, formal charge, exceptions to the octet rule, and determining the predominant structure of a molecule based on its formal charge. And in the 4th video, we're going to cover molecular geometry and molecular polarity. We talked about bond polarity in this video, for example, with our oxygen and our nitrogen. But this is only bond polarity, and molecular polarity is something completely different, and the way you determine the polarity of a molecule is based on completely different rules or regulations. Well, that's it for this video, and stay tuned for resonance, formal charge, and exceptions to the octet rule. Thank you. Goodbye.